Hello and welcome to our lecture number 4, where we'll discuss some related work on intercloud virtual networks. So the techniques that were discussed in the last slide tend to focus on a single provider virtual network. When you need to connect multiple cloud infrastructures together, it's difficult to do so because you cannot assume now that you can program the entire network infrastructure because you have different domains and different administrators across these different clouds. But these bring important use cases. For example, when you want projects that involve use across multiple institutions to collaborate, or when you want to deploy your own services across multiple clouds and be able to move them around, migrate between different cloud providers to get a better deal on a price, for example, or to get better availability and be able to migrate and deploy resources across multiple providers without changing your application significantly. So the challenges include the fact that you now have a shared environment that you may not control. For example, resources connected across the internet, you're not able to program the internet infrastructure. And if your traffic goes over public networks, privacy is important. So you need to be able to encrypt and authenticate your traffic so to avoid security leaks. And there's additional connectivity constraints on the public internet because of lack of IP addresses. Because security concerns, you end up having many domains that are constrained by firewalls and also by translation of addresses that's introduced by NATs. The problem is firewalls may block traffic based on a protocol, port, or host, and address translation makes it difficult to establish the kind of tunnels that we described in the previous slides that make it possible to create virtual networks on top of existing infrastructure. So for example, if you look at a typical network address translator, what it does is it allows a large number of computers, let's say of a single connected to a single domain like an enterprise or a university, to be able to connect to servers on the public internet. The challenge is every device that's connected to the internet today needs to have an address. And on version 4 of the IP Internet Protocol, this number is limited to about 4 billion, and we're running out of numbers. So to be able to connect resources to the internet, in many cases you have to have a number of public-facing devices, these network address translation devices, and they multiplex connectivity for a larger number of internal hosts. This could be your laptops, your desktops, etc. So in this example, we have a host with a private address that uses a NAT to connect to another public host. So this is typically a client, like a web browser. This is typically a web server. And in client-to-server interactions, this is typically done transparently with the use of a NAT. So the way the NAT generally works is your private machine sends a packet with the destination of your public host, for example, a Google search website. The NAT will take that packet and translate the source to be the address of the NAT and generate a new port for that connection. The destination is the same. What changes is just the source. The public host will take that request and send a reply. Now the reply will use the address of the NAT, the public address of the NAT, as its destination. And the NAT will keep memory, will keep information about what is mapped to this endpoint. And it uses that information to now translate the destination and deliver it to the host that initiated that request to begin with. So again, that tends to work well if you have a client on this side and a server on this side, because all the requests are being initiated by the client. But if you're trying to do tunneling and you have hosts that are not on the public internet anymore, let's say you have host A and host B who want to tunnel messages in a peer-to-peer fashion to each other, but they're both behind nets. So if A wants to send a message to B, he can no longer do that because B does not have a public address. So he needs to find out what is the address of B on the public-facing NAT device that B is using. And vice versa, B needs to find what's the address of A on its public-facing NAT. It can get more complicated depending on the way NATs behave, and we're going to get into the nitty-gritty details of how IPOP deals with NATs later on in our presentation. So there's several VPN technologies out there. There's enterprise VPNs, open source VPNs. There's commercial VPNs tailored to end user networks like Hamachi. Not easily applicable for many domains. Could be difficult to configure and manage, require centralized gateways, or in many cases you're looking at technology that's not open source, it's proprietary, and you cannot deploy your own. I'm going to focus on efforts, related works that looked at the problem of virtual networks in grid or cloud computing. And that dates back to efforts back in the early 2000s. VIOLIN is one of the first published overlay networks that targeted cloud or grid computing as termed in the day, basically allowing you to create virtual switches as part of your virtual network infrastructure and connect multiple computers across multiple providers in a seamless fashion. So it was a layer 2 virtual network that used virtual machines as endpoints. Similarly, VNet, a contemporary effort that focused also on layer 2 virtual network, extending enterprise network to access remote hosted VMs, much alike what we discussed for Amazon VPC in the previous slide. This is still an active project and focusing on integration with virtual machine monitor and high performance packet processing. Vine is another project here at the University of Florida, and it's a layer 3 virtual network that's managed, so you can establish layer 3 tunnels through Vine routers, and it allows you to establish routing tables and configure how you're going to handle nets and firewalls through proxies. So it's similar to IPOP in it being a layer 3 overlay, but it exposes the management responsibility to a user who controls the Vine network. IPOP started also in the mid 2000s with the Brunet implementation of IPOP. The idea was to start with a peer-to-peer tunneling network, and it actually started with a peer-to-peer messaging network, not just for the IP over P2P messages, but also for all the control and all the negotiation of tunnels. So it implemented decentralized NAT traversal with UDP hole punching. It was not a standard approach to UDP hole punching, but worked similarly to what stun and turn techniques that we'll discuss in the context of IPOP-tincan in subsequent slides. So the current version of IPOP can be seen as a hybrid centralized P2P system. So it uses a centralized system, which is an open online social network, for example, that exposes the XMPP protocol to do discovery and key exchange for endpoints. But it uses peer-to-peer links to create tunnels between endpoints in a way that bypasses a centralized gateway. Few reasons for moving from the previous Brunet-based overlay to the new tincan approach for IPOP include the ability for us to reuse a lot of code that came from the WebRTC domain, and also to reuse standards that became more and more available since the previous version of IPOP. Those include the XMPP messaging protocol and stun, turn, and ICE for NAT traversal. And a lot of this comes from the libjingle open source library that's maintained by Google and is used on applications like Google Hangouts. But instead of focusing on voice and video, IPOP allows us to tunnel general purpose IP protocol messages over the P2P links that we create. Tincan also features a modular design that separates the data path and control that's somewhat akin to the open flow approach to software-defined networking, but we'll see how it's different as we move on into more details of the IPOP architecture.